Alright, in this video I'm going to discuss the combustion analyzer. A combustion analyzer is one of the ways that we can try to figure out how much carbon, hydrogen, and oxygen is in an unknown hydrocarbon. If we have an unknown hydrocarbon, I'm on eraser here, hold on. Then what we mean by that is we don't know what the ratio between these atoms are. So what we can do is we can burn it in air in complete combustion. That will produce CO2 and H2O. By measuring the mass of CO2 produced and the mass of H2O produced, hopefully we can work backwards to develop a molecular formula for the hydrocarbon. So we have some unknown hydrocarbon. We're going to burn it in air. And we're going to produce CO2 and H2O. We're going to try to figure out the mole ratios of all of these things so that with that we can figure out how much carbon and hydrogen and eventually oxygen were in the original hydrocarbon. In this specific example, we had 25.6 grams of our unknown hydrocarbon. And when it was burned, it produced 52.8 grams of carbon dioxide and 14.4 grams of water. Now you might be looking at that and say, whoa, the mass of the products is way bigger than the mass of the reactant. But remember, it was burned in air, so air was used in this reaction as well. So let's figure out how much. 52.8 plus 14.4 tells us that the total mass of our products was 67.2 grams. Now if 25.6 grams of that came from the unknown hydrocarbon, that means 41.6 grams of that product mass must have come from the oxygen. Okay, now we know the mass of everybody involved in the chemical reaction. We can go to try to figure out the actual ratio between the moles involved in this chemical reaction. Or instead of thinking of it as moles, of course, we're going to try and think of it as the number of particles. To convert these things to number of particles or moles, we need the molecular mass. For the unknown hydrocarbon, that's been given to us, 256 grams per mole. For all the other ones, since we know their chemical formulas, we can find them. Oxygen, 2 times 16, or 32 grams per mole. CO2, 12, plus 2 times 16, or 44 grams per mole. And water, 2 times 1 plus our 16 for 18 grams per mole. So remember, moles is equal to our mass divided by our molecular mass. And so we can find the ratio of the actual moles involved in this particular sample. 25.6 divided by 256, that one's pretty easy, 0.1. 41.6 divided by 32 gives us 1.3. 52.8 divided by 44 gives us 1.2. And 14.4 divided by 18 gives us 0.8. So this is an actual ratio of the number of particles that are included in this chemical reaction. It's just not a useful ratio because it's not a whole number ratio. So what I'm going to do is divide them all by the smallest number to get it into a whole number ratio. Obviously 0.1 divided by 0.1 is 1. 1.3 divided by 0.1 is 13. 1.2 divided by 0.1 is 12, and here we have 8. So one of these reacted with 13 of these, reacted with 12 of these, reacted with 8 of these. And when I say these, I could have said reacted with 8 particles, or I could have said reacted with 8 moles of particles. It doesn't make any difference. And since both are a representation of the number of particles, this gives us a ratio of the number of particles. Using this now, I can go backwards to discover my actual values for x, y, and z. Carbon, probably the easiest one, 12 times my 1 here, tells me that I have 12 carbons. 8 times 2 hydrogens, or 16 hydrogens. And the tricky one, 24 plus 8 oxygens results in 32 oxygens. 26 of those oxygens came from him, so 32 minus 26 tells me 6 must have come from my hydrocarbon, Z. So there we go. And since I know this is the molecular mass, I know that that's the right number in terms of the actual molecule of this. Hold on, 32 minus 26, is that right? Yeah, that's right, okay. So I know that that's the right molecule for this right away without trying to figure out if I need to reduce or multiply it by anything, because I used the molecular mass right here when generating this. Now one more time. I'm going to find the composition of a hydrocarbon by analyzing when it's burned in complete combustion how much carbon dioxide and water are produced. I set up the skeletal equation unbalanced. Hydrocarbon plus oxygen goes to CO2 and H2O. Using masses, I make sure I have the mass of every compound that's involved in the combustion. And then convert to moles to make sure that I'm comparing actual number of molecules or particles instead of comparing mass. Find a whole number ratio, and then use that whole number ratio as the coefficients of the equation to work backwards to figure out how many carbon, hydrogen, and oxygen atoms must have been put into this reaction from the unknown hydrocarbon. So that's how you do a combustion analyzer question.